to my talk. So my name is Ernst Biersak, but in fact the person who really did the work and suffered through all this was Hadrien Hours, who was my PhD student. And I'm always very optimistic and naive, and I think, okay, there's so many nice things out there, we can just apply it, and then when you try to apply it, it always becomes very itchy. So what I want to do is I want to convince you that the theory of causality is something that could be useful applied to networks. And I also would like to talk about our experiences, that all the practical details are very, I mean, you need to address many different practical problems, and there's still lots of room to do. Okay, so if this works. So the outline, I'm gonna first motivate, show you a little bit of theory, not too much, and then apply it to a problem we have studied with colleagues from Polito di Torino, who gave us very nice packet trace data that we crunched through tstat in order to get lots of metrics and then feed it into the model. So this was in fact the very last, the application study was the very last piece of work Hadrien was doing, and then I draw some conclusions. Okay, so every time you look in the newspaper, you see some causal statements. Today, I looked up Le Figaro because it's the only newspaper they give me in the hotel, and it says, if you are older than 65 and you exercise, then your risk of getting Alzheimer is lower. So there's some kind of causal statement. In fact, in economy, they apply this recipe of austerity for 20 years, and always say we need to turn the screw a little bit more and the economy is going to be better. Okay, so, well, is it going to happen? Would policy decisions be better if we had people being enlightened by causal theory? I don't claim this, because I think economy and real life problems are way too complex, but maybe for very simple statements, it could show that we even don't have enough variables, or they are what's called confounders. So, okay, so there is really one person behind. This is Judea Pearl, who is 80 years old, and he has been driving this with other people, but he's really the soul. And in fact, he's quite a character. He hasn't lost his accent after 50 years living in the US, so I want to show you a little bit of video, because he is still going around at 80 years, very active, so I admire him. So, and he gives tutorials, and he is like an evangelist. So I'll show you a few minutes, because he really points out.
There's also a machine learning problem. For what I learned by looking at here, the idea is that machine learning is an attempt to find a useful representation.
Can you hear anything or not?
That data.
Where's can help me
if you
somebody?
find a good model for the data, then you have accomplished machine learning.
First of all, he talked.
This is not the paradigm that I'm going to talk about.
Can you help me?
This has been 150 years
I'm
of
not
statistical.
sure, but this is audio in. Do you have a proximate?
I have no.
We have to quit.
Here, there's a cable. Okay.
Because we are dealing with modeling reality and not with modeling data. This is what.
There's another remote, so can volume. Yeah. Can you hear anything? Okay. No, okay, so I stop. In any case, he talks first about conditional probabilities, and he talks about the Santa Claus, and he talks about what we get out from existing.
Estimate the mean. Or estimate.
I have the volume maximum. Okay, so I'm gonna stop. Okay, but he is really a character, and I just wanted to show you a few minutes. So,
and it is in a statistical.
Does he stop? No, he doesn't stop. So he's the Santa Claus in my school.
Because you have an expression for it.
No, I'm gonna kill Chrome. So.
The query.
Okay. In any case, so his. In fact, I have a resume. So he wrote books, he writes memos. He has always just one PhD students, but he solved a large number of problems, and he's complaining a lot. He had lots of frustration. He says statistics has completely screwed up the minds of the people, and since they don't have the right mindset, and in fact, I think at the end this can be like a philosophical conclusion. If you don't have the right language for your problem, you either use the wrong language or you somehow fail. So, and this is what he claims what all the statisticians who just did conditioning did. And he got at the end a Turing Award. So he was, at the end it was recognized. Okay, so if you read his book, the book is very general, doesn't make any assumptions about what kind of distribution, discrete, continuous, anything. But in order to apply it, well, you need to do certain things, and this is difficult. He says one of the problems people have in statistics is this what's called Simpson's paradox. In fact, I don't know if anybody knows it. He complains, for instance, you don't find this in any performance book. There's only one Wassermann, and I think Le Boutec has it in. So you do some drug treatment. You have a treatment group and you have a control group, and you look at all patients, and you see in the treatment group there were 130 people, 70 it helped, so 54%, and then you look in the control group, it was the same size, and 60 were fine and the other one not. So you're saying the drug was effective because the percentage of success is higher here, okay? Then you look at this table, and in fact what you conclude is in both cases, so 20% success, 25% success for the placebo, and 75% success and 80% success for the placebo. If you look at gender-specific results, you get to the opposite conclusion. And statisticians have been struggling with Simpson paradox forever. And what should you do? And they try to frame it and so on. And in any case, you have an idea why we get to this result. Okay, there is, okay. In fact, what we did, we did some conditional probabilities. What is the recovery given the drug was given? What was the recovery given the drug was not given? So this is all conditional probabilities. So this is what Pearl calls seeing. We take the data and we try to get something out. But in fact, something strange happened. So there were, in the female group, the number of people getting the drug was much higher than getting the placebo. So it's 1.6 times. And in the male group, it was different. Okay? And this kind of explains this. So I don't want to go in. He just says the correct solution is you need to look gender specific. In fact, because gender is a confounder, which if you don't take into account, you don't get to the right conclusion. And statisticians have been struggling. There's a page that shows this. Other cases, there's a long history of this thing. And the question is, how does causality help us here? So with causality, it should become immediately obvious what is the problem. In fact, this is the thing. He introduced what he called the do operator. You can ask the question, what is the probability of lung cancer given that somebody smokes? So what we do, I take all of you, okay, I look in your medical record, and then I check also if you smoked, and then I can answer this thing. So based on observations, what we see, seeing, okay. But he says this is not the same as what is the probability of lung cancer given that we even make Fabio smoke who never touched a cigarette. So we have a completely, we are not talking about the same population set. We make now everybody smoke. So this is the do operator. We force people to smoke. And if we formulate it like this, we get the right conclusion. And in fact, what he has developed is a do calculus. And this is not equal to this. And how we get from the do calculus, how we can crunch stuff and get results, he has developed a model, basically causality between variables is represented in a graphical way. And you can see then how you manipulate this graph. And when you can switch from do statements to causal statements. In fact, there are 3 theorems. I'm going to list them. I'm not going to explain the theory, but I just want to revise it. So Simpson's paradox is a paradox if we misinterpret this as this. Okay? We want to really answer what is the recovery if we give a drug to somebody. And when we had this problem, we just had some sample population, and we tried to extract information from there. Okay? So this is not the same. Okay. So, and in fact, so this is a graphical model. We have a gender. This is the co-founder. This is a factor that impacts both the treatment. More women were treated than men, and it impacts the result. So if you model it this way, it's obvious. And if you ignore gender, you get it. And this is a typical sentence of his. You really need to read it. It melts on your tongue. I mean, it says it's like, driven by healthy causal intuition, yet culturally forbidden from admitting it and mathematically disabled from expressing it. The mention. So, okay. He has been suffering through probably for 40 years to get recognition, and he's still actively giving tutorials in order to teach these things, because he really thinks there are what he calls many blunders because people are not managing this concept. And hopefully with the Turing Award, he has got more recognition. Okay, so we have a set of variables like, as I said, age and physical fitness or exercise versus getting Alzheimer. And then you can, between these variables, you can have relationships. They are unrelated, they are causally related. So X1 has some impact, like there's this famous case. This case here is my grass is wet. If I turn on the sprinkler or if it rains. Okay. Rain is a variable, sprinkler is a variable, and the outcome is, so this is it's called a famous V structure. Okay, and there are these kind of relations. Sometimes you have these things which are more. Here you have a common cause. We had this was gender impacting both treatment and outcome. Okay, so this is, and then you have the language. You talk about parents, ancestors, and this, and well. People had before other ways, they had structural equations, but using this graphical calculus, you will see afterwards for our CDN study, we have a graph with 19 nodes. And you see very nice relationships between different variables. And then also you see, in order to answer questions, how you need to manipulate the graph. Okay? So you talk about descendants and so, okay. So the issue really is what's called identifiability. How do we estimate this from data? So like at the end, the question is, in my CDN talk, I have 2 classes of customers. I have customers of using the ISP's DNS and customers using Google DNS. And I can ask the question, what would be the performance of the people who have been using Google DNS if I give them the latency, the round trip times of the ones seen by the ISP's customers. So I do something, and then how do I get the result? So I'm not collecting any new data. I had a trace. I had 7,000 connections. I had basically a matrix of values, and I have my model. And I'm not collecting new experiments, because in networking it's complicated. In smoking, you cannot force people who don't smoke to smoke. But still, with this thing, you can try to answer certain things, which you couldn't do before. Okay? So here you have identifiability. And okay, so this was, I'm going to come back to the theory when I need different pieces, but I'm not going to, I don't teach you the theory. I just try to get you interested maybe to study this, because in fact today there are very few courses where this is offered. I get back later on where the groups are who do this kind of work. So I mean, a telecom network is pretty complicated. Doing real experiments, I mean, Google can probably afford experiments in redirecting people to places further away, but usually doing experiments by physically displacing equipment or this kind of thing is very hard. So we really would like to collect some data and then ask some what-if questions. So these are the kind of questions. What happens if we would do this or something else? Okay? And so, like troubleshooting, understand observed performance, and predict strategy outcome. So what would happen if this CDN node would be closer? And the constraint I really have here, I'm not doing new measurements. Okay? Sometimes I might not be able to get the answer. The model also tells me, given this data, you cannot do it. But often you can get there. Okay? So what is the procedure? Well, you define your system, you observe your system. Then, this is a pretty crucial thing. You infer your causal model. You basically try to infer this graph. And when you have the graph, you're going to use this calculus, and you're going to ask questions, and you manipulate the graph in order to show you how you're going to do the mechanics of the calculations. Okay, so what is the setting? We have the Akamai CDN. So I click here. I want to read Le Monde. Basically, Le Monde sends me for the full PDF to some Akamai node. How does the Akamai system decide where to redirect me? They take usually the IP address of my DNS server. It could be the DNS server here, or of my public ISP, or if I use Google's DNS, and they try to measure a match distance. It's a very simple model. They can include more parameters, but let's assume they try to always match to me the CDN node that is closest in terms of RTT to the DNS server who was resolving my queries. The argument being, if the round trip time is smaller, then TCP cranks up faster and I get better performance. Okay? And so this is what's basically said. We use DNS. In fact, this can work very badly. Like in very early times, AOL had one DNS server in California, and everything was resolved basically through this DNS server, and then the assumption was the customers would all be close. So the assumption that the customer is necessarily close to the NS server can be wrong, and if it's wrong, it leads to bad decisions. But if you do this level 7 redirection, you end up, except now you have possibilities of basically passing your IP address through and giving hints, so these things get improved. But this is not the goal. Okay, so we have a situation like this. This is me, my client. I type a URL Le Monde. It goes to the DNS. The DNS, this is my ISP's DNS. The DNS resolves it, basically asking the authoritative DNS server of Google, and then and he resolves it basically trying to give me back an address of a node, of a CDN node that is close to me. Okay, so this is the case of I'm using the ISP's DNS. Then the second case is I use the Google DNS servers, and I do the same. And it turns out the Google DNS server might be further away from me, so the match might come out differently, and what we see, in fact, in the data is there is a difference in performance. Okay? So, okay, so what is the question we were asking? We study the impact of what kind of DNS server we are using. So this is a categorical variable. It's either ISPs, we call it local DNS, or Google DNS, and compare the performance for customers who download something from Akamai using either one, and predict the performance if a user of DNS service A, what performance would he get if he would have used the other DNS service. Okay? And so this is a pretty complex system. We see we have, when we extract from T-start all the information, we get lots of data, and we are not able to do controlled experiment. A company might be able to do it, but still it's very expensive. And if you can avoid doing it, it's probably preferable. And in fact, what we do is we try to apply causal inference, where we model the interdependencies between the variables, and then we manipulate the whole thing. Okay. Yeah.
I had a question about the performance prediction is basically a regression about...
No, it's not regression. It's not regression. It's coming. It's
just a delay, or
no, it's more complicated. You really need to wait a little bit. And okay, so yeah, please.
Not only technicalities of the prediction, but essentially what is the actionable knowledge that we want to extract?
You see what I extract. I go through, I show you all the variables, and I show you everything. Okay, but if then something is unclear, please come back. So the first thing is I want to infer this model, and it's represented as a Bayesian network, which is nice, it's concise, intuitive, and then I want to evaluate effects. Effects is we change something. What's the outcome? Okay, so in very simple terms is I have a set of features like 4 variables. This can be age, do I exercise, do I not, do I read Le Monde or some other newspaper, and I do observations. So these in my case are basically variables like congestion window, DNS service, and so. And for each connection, I get basically one line, which is the actual values described. Okay, and I feed this into some magic, and this magic derives my model. And I have to say a lot about this magic because this magic is pretty crucial. The magic is in theory pretty nice, but then when you really apply it to data, you need software, you need tools to do basically conditional independence tests, and there is lots of practical difficulty. It's not Perl has solved it theoretically, but putting it into place is tough. But people also work. So one of the algorithms so this would be a model that the variable x1 influences both x2 and x3, and these two influence x4. Okay, so the algorithm one is called PC. In fact, Perl was doing the theory. He also developed algorithms, but he never built real tools. There's another group in CMU. They're in the philosophy department, sprites, spines, and they had students who really built also tools. And they implemented these tools, and they're available, and we used them. So by using their what's called PC algorithm, you get the model. Each vertex is a parameter, and each edge is a causal dependence. Okay? So how do you go about? You have no idea of what are the relationships. So what do? I'm going to show you first. This I don't know. I start with a fully connected graph. So you can imagine if you have 19 variables, this graph has 19 times 18 links. And in the first step I do, so this is my skeleton. In the first step I do independence check. Is x1 independent of x2? Is x1 independent of x3? Is x2 independent of statistically independent of x3? And if the answer is they are independent, then I cut the link. If they are not independent, then I leave the link. Okay, so this is the first step. It's unconditional independence. Then I do conditional independence, conditioning set size being 1. But okay, do the same test, but imagine you have a graph where some nodes have 10 links coming in. I get conditioning set sizes who get bigger and bigger. So in my case, I'm almost done. And then I have still an unoriented graph. And then I need to try to orient the edges. There are some rules. I'm not going to tell you. There's some magic. Sometimes they don't succeed in orienting. Then they show you some kind of dotted lines, because there could be also a situation where they are mutually dependent. But they try to. So this is all well established in theory, how you do this. And this is really the key problem. So now do this. So I say to Hadrien, OK, download this little software and run it. OK? So he does it. And he gets complete nonsense. OK, why? Because what independence test do you use? These tools implement what's called the Z-Fisher test that makes assumptions about the data, namely normality and linearity. OK. So the practical side of this thing is extremely crucial. And if your data are not normal and linear, so what we did, we created synthetically values. We had a model. We said, OK, this variable is 3 times the value of this one, plus. So we created linear, quadratic. And we tried to see, and immediately, no magic. If these assumptions don't hold, the graph is jumped. OK? But for instance, there was a guy, Kun Chang. There's a group pretty strong in Tübingen. It's Schulkopf, who did lots of support vector machines. He is director of an MPI. And in fact, today he does mainly causal reasoning. So he has like 4 group leaders. And Kung Seng is now, in fact, he's a associate assistant professor in Carnegie Mellon. And he built a tool called kernel conditional independence, where he doesn't make these assumptions. OK? So he was very nice. He gave us the tool. It's implemented in some code. Unfortunately, if the data set is large, then you have numerical issues. The whole thing crashes. And even if it doesn't crash, Z-Fisher took 1 minute, and the independence test takes 3 days. OK? So you see, immediately you run into very practical issues. So I'm not saying what we did then. We bootstrapped the data, we sampled, but this is a typical case where if you do bootstrapping and you take a subset, you can parallelize things. So yeah.
Can you give examples about the edges that you have in your graph, like concrete examples?
Yeah, it's coming. It's coming. OK. So in any case, Hadrien was not a big computer wizard, so he suffered through this in kind of the practical side, because it made it very difficult. OK. So now I come back. So I'm giving you a little bit of theory to come back to the practice now.
How many variables?
I'm going to show you. But I gave you the theory right before I come now to the practical case. So we have this network. Somebody captured data here. So it's on the path. We have part of the path that we call the internal network. It's like from the POP to my home, and then the big external network. And T-stat is nice enough. It gives us round-trip time estimates for both sides, which kind of is crucial to understand, because we use these variables. OK, now look at these variables. 19. This is what we feed in. We feed destination IP address, DNS server, day of week, 2 days. We had a work day, time of the day. ISP RTT. What's the RTT in the local side? Standard deviation, number of hops. What's the RTT average on the long haul side? What's the number of hops? How often see we receiver window 0, which means stop, TCP. So these are TCP variables. Maximum receiver window, minimum, congestion window, retransmission score, retransmission timeout. And you see, these are all different things. These are Boolean, categorical. These are units are different, number of bytes. And what we are really interested in is the throughput. OK, we feed this into the thing, and we get this graph. OK? So
What is the thing?
We feed a matrix with 19 variables for 7,000 connections into this statistical, into this algorithm that derives
The PC algorithm?
PC algorithm derives from the PC. It's not the PC because we had to rip out, for instance, the independence test because it was making assumptions. So we were using parts of the PC and we were plugging in new pieces that were doing a different, that were not making the assumptions of normality and linearity. Because why? So we had 7,000 connections as samples. So I have, for all these parameters, I have 7,000 values. And the traces were collected at 2 days, Sunday and Thursday. And these are the histograms. So you don't see any normality. It's multimodal. It's all sorts of things. So, and some are continuous, some are discrete. So this is why we couldn't get anything going with the Z-Fisher test in the PC algorithm. Okay, so this is just it's an optical view of the situation. Okay, so what are the software package? The Carnegie Mellon people have a package called Tetrat. There are multiple things in. There is a group in ETH Zurich. They have an R package called pCalc. They still, and there's Murphy. He has also this nice book about machine learning, 1,000 pages. He also has a nice chapter on this. So he also has basically makes the same assumption. So we couldn't use any tool out of the box. So, but by contacting Kung Seng, he gave us his test, and then we plugged it into some other tools, and we tried it. So we tried lots of things. I give you references also that show what we could achieve. Okay, so really the step from theory to practice is really the hard step. And in fact, there are attempts in other domains. There are attempts in genome. They want to find what gene to knock out. And there are attempts, but in networking, there was just one other piece of work. Okay, so this is really the graph. And depending on what software you use, you get slightly different graphs, and you need to use domain knowledge. So I'm not going to go through the whole thing, but okay. This is throughput. What parameter is impacting throughput? So I just tried to show you a couple of things. The retransmission score is impacting throughput, of course. It makes sense. Okay, the minimum congestion window. Okay, the maximum, the minimum. The retransmission timeout. Also,
we are not looking for the Markov blanket.
You mean
in this
you can you can have more than one graph basically. There are equivalences, and it's giving you one. Okay, but in terms of how you manipulate for your purposes, you should get the same result. But of course, this I skipped completely. The tool. There could be multiple, for the same set of data, there could be multiple graphs who represent the thing. And I show you one.
Okay, and in this one, how you choose the most, let's say, the metrics with?
No, we tried, we had more metrics, we removed some. Sometimes you see the number of bytes is not even connected, so we let it in, but it doesn't mean anything. See? Okay, but so you see also the ISP, the average RTT in the long haul has an impact on the throughput, which is also reasonable because TCP is having a feedback loop. And then you see interesting things here, like the day of work has an impact on DNS. Why? Because the users on Thursday, more people used one DNS resolver, and on Sunday, more people used the other DNS resolver. So and I have this one. So the graph found stuff. It found stuff that you expect. It found some more interesting stuff. Also, the time of day has an impact on the RTT if the network is more loaded at evening times. So, well, at some point, you have to use domain knowledge. First of all, we used more domain knowledge to exclude. For us, it was ringing a bell for a long time. We got some graphs, and they look completely weird, and we couldn't make any sense. So then we tried to keep on. And this is something to us that, okay, looks reasonable and gives us some insights. And this is the thing we want to use then to compute the effect by acting on things like what Perl calls mutilating. So I take a variable or I cut a link and I set the value of this parameter to a fixed. I do the do operator. Okay, so you see like causal relationship between the day of week and DNS, because on Thursday 72% used the local DNS and 28% the Google, and on Sunday it was the opposite. We can only speculate. The data we don't have. We got the data from Polito. We can't go back or knock on the door of the users and say maybe on one day it was grandmother and on the other day it was somebody who was a cool hacker. I don't know. So I don't have. And you also have you have a causal relationship from what DNS service we use to the INET RTT. So this is also important. So if you use one DNS service or the other one, the long haul RTT you get for your connections is not the same. So this is something that kind of confirms that type of DNS service you use can have some impact on your performance. Okay, what other people showed in IMC papers. Okay, so, but this is a pretty complicated thing, and it took really just pure compute time. It takes a pretty long time. Okay, so, and this is the histogram of the external RTT. So you see, for the users of Google DNS, there's more mass to the right. Okay, so they have a higher, they have higher values in distribution, and they also have higher values in average. Okay. So now, so this is I come back a little bit to the theory now. So I have shown you what graph we have. And now I say, what does the theory do? The theory asks questions like, given this graph, I can ask question, what is the causal impact of setting the value of this variable to x? What is the impact on x4? Okay, and this is in Perl's calculus. This is formulated like this: do. What is the probability that x4 has the value of y, given I set x2 to x, okay? This is called an atomic intervention. And here, in fact, I'm not showing you why. It all resolves to conditional probabilities, and we are, for this model, you can really solve it, okay? Let's make it more complicated. So these are the three basic statements. What you do is basically ignoring observations. So what we do is here, I'm not going to explain you this. Y is independent of Z conditioned on X and W in the graph where we remove all incoming links on X. So this is the notation. We can ignore observations. We can do what he calls action observation exchange. So here we remove the do operator. Why can we remove the do operator? Because Y and Z are conditionally independent. And in fact, what I write, first the formula where you're going to see the formula I get for my problem. It has 2 or 3 do operators. And at the end it has 0. So I apply these 3 rules, and I get, using my graphical model, I can check for some conditions to make sure I can apply these rules. And then at the end, I have only what I see, conditional probabilities or even just regular probabilities. Okay? Okay, so the question is, what would have been the performance of a user served by the local DNS if he would have been redirected to a server, to a CDN server corresponding to a server the users of Google DNS were redirected? So what would have been the performance if he would have been redirected to a server further away? Okay? So how do I write this? This is the statement. Yes?
Just for
yeah.
Sorry for interrupting. I don't get the point of the question. So this is part of my previous
The question is,
actionable knowledge.
the question is like,
This question is interesting. This is the first question.
I want to show you at the end. I show you the result. I show you the result. I show you the result. If the users of the ISP's DNS would suffer the RTTs of the ones experienced by the users who use Google DNS, their mean throughput goes down from 3.5 megabit to 3 megabit. They have a 14% decrease. In distribution, it goes from here to here. I can answer in distribution, what is the impact? Purely out of observational data. And this is an interesting question. So if you have a choice, you say, I don't like my ISP's DNS, you know what you pay. You pay a penalty.
But this is dependent on the settings that you have and on the data that you used. It's not like a general truth, is it?
It's the set of data where I have both populations. I get this out of data. If I measure something in France, maybe I get a different result. But it shouldn't be surprising per se, because the intuition confirms if you have larger round-trip times, you get, for huge objects, you get lower throughput performance. But what's the interesting thing is I can fully manipulate the whole system and I can quantify this exactly. It's not just, and I don't need to do any new measurements.
Under the assumption that all the latent variables are already in your graph.
But even if I have forgotten some variables, if the impact variables I have in the model, the ones I have in the model represent, kind of summarize the other thing. And if I have really latent variables, I get a graph where I cannot resolve orientations. But of course, this is the first study, and you're welcome to improve this work. Okay, but in any case, so, okay, are you happy? I want really to be happy. You can harass me for the next hour, because it's good, because the other people are just friendly and unhappy, and you are unhappy and harassing me. Okay, so I go back. Okay, so I go back. I show you the mechanics. Okay, so first, the whole mechanics was done by Hadrien, so I'm not really mastering all this, but I thought, what is the throughput given that for users of the local DNS, if now we do the do operator and we give them the distribution of the throughput seen by the Google DNS users. So this is the distribution follows of the RTT follows the one where we operate on the DNS and we set it to Google. Okay? So, we do an atomic intervention here because we have an atomic intervention here. And so how do we get this formula into something more practical? In fact, this is the original formula. We just apply one of these three rules in each step, depending of the calculus, in order to simplify things. You see, for instance, here we go from, how does he call it, from action to observation. We remove the do operator, okay, in this step. Okay, so here are the rules. First is we apply what's called the backdoor criterion because they are independent. B is also, and C is basically applying a piece of Perl's book. Okay, so you manipulate this, a calculus, if you know the rules. This is not the difficult part. The difficult part is getting the graph, formulating the model, and I mean, you have three things in your do calculus. This is not the hard part. Okay, so, okay, you have at the end this formula. You still have marginals, and he needed copola to drill. So he still had practical problems afterwards to get really results, but I'm going to skip. This is kind of the outcome, okay? He gets at the end, he can show like, So the further to the right the distribution, the lower the performance, because you have few. No, yeah, you have fewer values of. No, hold on. Pre-inter. Yeah. Okay. Here we had. Is it right or is it not right? Is this curve better than this one or the other way around? It's the other way around. What? But it shouldn't be. So this is why I'm asking. Look, this is post-intervention. Because in red you have 40% who have 5 meg or more, and in blue you have only 30%. So I think the curves are messed up. In any case, we get the result in the distribution, and we get the result in the mean. Okay. Okay. So, in fact, so this is again kind of summarizing what Pearl also said. What do we do in statistics, and what do we do in causality? Statistics is about association. It's about correlation. We model distribution of data, and we predict by conditioning. We basically, well, conditioning is nothing else than reducing. So if I condition on the sex, basically I reduce the population of the people here on either just female or males. Conditioning is not what we need for causality. In causality, we force everybody to smoke. Okay? So he says the mechanism generates new data. Okay? And we do this. We predict results by intervention, by really forcing people to smoke, and therefore we get usually we get this discrepancy between what we see and what we do. Okay. Okay. So concluding remarks, several. I think it's a very powerful idea. It's you should try it. The theory is really nice because it's completely non-parametric. It doesn't say anything about what nature your distribution is. The independence tests are really one of the key things, and you need to have the right tests. I think for somebody, it would be a nice interdisciplinary problems, people who understand well theory, some people who are pretty good in like spawning out like the test to 100 machines, merging the results, because we had 7,000, we have data from 7,000 connections, so we are not talking about big data yet. We had really a small data set. What was also nice, it's a really small community and people are extremely friendly, so we almost interacted with everybody. So Pearl has written the book. He had a student, Elias Barnbaum. He explained us counterfactuals, so he is now a faculty. Hadrien was going to these people in CMU. They do every year a summer school, so he went to the summer school, and then he got some help. These people also wrote a book. And then there's it's an important group now at MPI Tübingen, Schulkopf, Sang, and they exchange people with Zurich, so that people go back and forth. So you have some Marilis Mattis and Peter Bühlmann. You have statisticians in ETH Zurich also who are doing it. And on the jury of Hadrien, there was also here from France, Michelle Sebag. She's in the Tau INRIA group, so she's CNRS. And in fact, Kung Seng also was on Hadrien's jury, so the world here is really small. It's a pretty small and friendly group, and they really appreciate when you try to make some progress or post them a problem, and you get feedback. So general lessons, that's a big step from theory to practice. The first thing we tried to do was to build a causal model for Dropbox. So I was very naive. So I said we capture a packet trace, and then we do the same exercise we did here on Dropbox. But there is latent variables. So Dropbox had some mechanisms to adjust rates or chunks things into blocks we didn't capture. So we had a graph and didn't get anything out. Why? What could we do to make Dropbox downloads faster? Okay, so we realized it's a chapter in his thesis. It reads pretty interesting, but it was a failure, complete failure. And then we said, okay, can we do something? And then Patrick Loiseau came in on saying, okay, maybe you build synthetical models. You kind of create your own data with dependencies, and then you check what the tools do. And you create data where you violate linearity and these kind of things, normality, and then you see. So then it was a more principled approach to see really what the tools can give us if we know what's the structure. And if you have a little bit more confidence, then you can go back and say, okay, let's try another real problem, which was the CDN case. And in fact, really lots of time was spent all this. I mean, if the whole thing runs once, you get the results soon. But validating hypothesis, knowing your data, what's in, and if you have something missing. And also cleaning maybe the data a little bit. So this, and then adopting the methodology, the tools. First the test, and then also parallelizing it in order to make it run faster. Okay, so just one. So I talked about things you would expect getting out, but there's one relationship, just one. DNS to CW min to DNS. So this relationship kind of is a little bit surprising, that the DNS server, the choice of your DNS service also has an impact of the minimum congestion window. So we couldn't really resolve it. It could be that there were configuration differences or so. But we saw certain things that, okay. And there is some impact, okay. And we were asking another question about which I'm not going to. But it's also, of course, so we got the data set. The people of Torino were very nice. But in general, in all my life, to really work effective, it's always, I say, to go back and do more measurements or tweak the thing a little bit. So if somebody gives you data and say, do something, then you have some questions. So why is this? And we couldn't really ask anybody.
Maybe it was the topology and the routes, something that you don't have.
Okay, yeah, in any case. So, but even having maybe somebody who runs this system confirming us certain hypotheses or saying, no, we did something else there or so. But in any case, so, and we also did, I didn't present this because this is a real study. We also did one thing first. We modeled FTP download. So whenever I was traveling, I connected my laptop to Eurocom. I was downloading huge files, and we were capturing the trace. So we did controlled experiments there. If we had questions, then we could maybe do more experiments. But here, it was really to kind of make a case. You get a set of data, and you try to infer something, and you are not able to change the configuration. You're not able to do more experiments. Okay? So there are 2 papers out. We are pretty proud. So if you bang your head long enough, there was a special issue on just on this with all the big shots as editors, Schölkopf, Pearl, and we got our paper in. And so it's about, and these big papers, they have large appendices, which is really nice. So you can do all the things which you usually don't tell what you did in order to convince yourself. We have like the paper is 45 pages, but it's 20-page paper and 25 pages. So we show other graphs we got that look pretty weird. And on synthetical data where we know what the structure is in order to show really the independence test is key. And this is the work I presented. It was an ITC paper, and now we have a journal paper where also we have all the what we did in bootstrapping, how we then consolidated the independence test on the subsamples, where we kind of, because otherwise if you just present the result, it's not somebody takes it and he applies it. So we show really what's underneath. And so some of the slides, in fact, when I was preparing the talk, the first thing was I just show you 20 minutes of Judea Pearl's talk, then I'm already done half. So fortunately, I didn't rely on this. But then I found also slides from this guy. So sometimes you see it was PDFs copied into. And he was also a student in Tübingen. He's now a professor in, and I copied some, so I should give him credit. And the most credit goes to the co-workers, in particular Hadrien, who is now a postdoc in Lyon, and he doesn't want to do causal stuff anymore. I don't know. I say you're the expert now. You should go around and evangelize, but he doesn't want to do this. Maybe he had a bad experience with me. But yeah, so okay, you have to ask him. But in any case, I think it's an interesting tool, and I think also just knowing about this theory, then when somebody presents you some stuff, it makes you a little bit more critical maybe about when people draw assumptions without really using lots of rigor in modeling these things. And okay, this is 50 minutes, so I stop here. And if you have any questions. So I stop here right in time for the ones who need to see the most important man, Macron. Watch out for him. Every time I see him, he fixes his tie, so I think he has very nervous hands. So check out how many times he does it today. But no, but it would be interesting to find a causal model. Is it just ambition, or is it something else? Maybe he no, but he looks out for snipers all the time. So, so he holds all. It's okay. So, but it would be interesting. Maybe you can ask him to get the real answer, because I can just hypothesize. Okay. So, any questions or comments? I'll be around. So, these papers, if you Google, you find them online. If not, you can ask me. I'm really happy to show. And we try to profit from the extra space, really to put in enough of the details to help somebody understand what we did, and if you want to do something similar, how you can do it. But of course, you can improve it significantly, particularly the practical side. Okay, so these two. So this is out, and this one is conditionally accepted. Okay. So any questions or?
Yes. There is a difference between cause-effect and the causality theory that you presented, right? Because you are still dealing with statistics to prove the dependencies. I have to go with this.
Yeah, but okay.
I'm not sure that the cause-effect and the causality you are defining are the same thing.
I think so. I mean, if you ask health questions like, or you can ask questions, there were a practical question like this. The Simpson's paradox was in Berkeley a real case.
No,
Berkeley.
This I understand.
But you mean for? Okay, sure. For cause and I don't know. It's a philosophical question. So read his book. He's a very wise Jewish man, and he has lots of insights, and particularly his talks are always entertaining. So okay.
About the causal graphs,
yeah.
Can you perhaps use them to give at a glance some sort of feeling for how the dependencies are between the variables in your system? Like you have some sort of very powerful way, I think, to present what goes well, what goes worse when you change something.
Yeah. In fact, when I went to, so we were at some point, we were very desperate. And so I said, we need to get some help on board. So I went to Zurich and I met this young Professor Marie-Louise, and she said, oh, you have only 10 variables. This is very small. I work with people in genomics, and we just want to get a rough idea of how things look if we want to knock something out. Like maybe there is some crucial point, we have no idea what it is, and then we get a very big causal graph, and by looking at it, we see maybe there are some local places where if we would influence some relationships, it would have a big impact. So, yeah, if you, yeah.
But even the graphical representation you uploaded for the network suggests some linearity and kind of pair-to-pair relations between the variables.
But if you look at the TCP formula, it's already so. The TCP formula is the throughput is inversely proportional to the RTT in the square root of loss rate. So that's not linear. Even the simplest model in TCP has already nonlinear relationship. It's I don't have anything to write. It's a constant. Its throughput is equals C times maximum segment size divided by RTT and the square root of P. So it's non-relational.
I was referring to the graph.
To the graph. Why do you think there? Okay. Here.
Yeah.
What do you think is linear? And what does it help us?
You know, I'm not even sure if there are, let's say, groups of variables that are actually altogether affect in a significant way or cause something else. So here, you know, it's a simplistic.
Yeah. We tried this. In fact, there is some work where you can kind of show how X1 influences X. Hadrien tried to work on this also because this would be also interesting to find the most important relationship. But there he kind of got stuck. But this is, I think, still open work. He did something and then it turned out to be, we showed it to other people and they say it's ugly. Okay, but he tried to do this also, yeah, because it would give us some other interesting insights, yeah.
You said you use domain knowledge in which parts?
Well, I mean, to validate, so it doesn't look completely, we got other graphs that, well, the fact that I see really all these variables that I see in the TCP throughput formula.
So it's just for interpretation, not for like directing the results of the...
No, not directing. The directing, I ask questions maybe I want to ask, and we were asking questions we could also answer from the given data. But it's more like look at these things. So, I mean, we saw all the direct links into throughput, and they kind of looked right to us. Losses, congestion windows, RTTs, both in mean and variance. So,
can we get this graph using only domain knowledge?
No, things like this I would not have. I mean, how does this relationship come? If I had not done, I mean.
Like I said earlier, it's maybe because it could be that the topology that you don't have and the routing may make that you.
Well, I'm stuck here, so we did another study on where we controlled things, where we could maybe make modifications in order to have this kind of iterative cycle. Here I don't have it, so I cannot, I'm stuck. Okay. The only thing I hope I didn't say anything blatantly stupid about CDNs and DNS. But, okay.